This lesson is going to help us determine if a function is linear or nonlinear when we're looking at tables. We do see graphs here, but they're just as an assist for us, just to support what we find. So the first thing you want to know is that when the rate of change is constant, that means when you actually have it stay the same for pairs of inputs and their outputs. So that would mean your inputs are always your x values and your outputs are your y values. Then the function is a linear function. We know that every linear function is in the form y equals mx plus b, or it can be in that form. So we're used to finding that slope and that y-intercept. Remember, the y-intercept is where it crosses the y-axis, and the slope is the rise over the run. So we're going to determine if a function is linear, and we're only going to look at the graph or the table for this. So I want you to put your x at the top for your inputs and the y at the top for the outputs. And what we're going to check is whether our change in y over our change in x is the same every single time. So watch how I do this. So my change from 2 to 4 is adding 2. And my change from 5 to 7 is adding 2. So the y over the x would be 2 over 2, which reduces to 1. Then my change from 4 to 5 is adding 1. My change from 7 to 8 is adding 1. So my change in y is 1 over 1, which is just 1. And now my change from 5 to 8 is adding 3. And my change from 8 to 11 is adding 3. So again, that change in y over change in x is 3 over 3, which is just 1. So is it linear? What you do is you look and you see if these numbers are all the same, then yes, it is linear. So you would say yes. If it is, we can write an equation. We're able to do that. So we would find our slope, which we did. It's y equals mx plus b, but we found our slope to be 1. So our slope is 1. So you would say y equals 1x. And now to find your y-intercept, you need to know that you are looking for that value where your x is 0, your input is 0. So imagine if you went back in time 2 spaces, you would be back at 0. And you know your slope is always 2 over 2 or 1 over 1 or 3 over 3. So if you're having to go back in time 2 spaces to get from 0 to 2 would be plus 2. You could also go back in time 2 spaces here and that would give you a 3. So your equation will be y equals 1x plus 3. You can see this even better by plotting it on the graph if you would like to. You may also just watch me plot it. These are your x's, these are your y's, and I would plot 2, 5, so 2, 1, 2, 3, 4, 5, 4, 7, and I know that I have a slope of 1, so I'm just going to move along 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, so that would be here. And I know at this point I have a slope of 1, so I could kind of go down and say, oh, that means I start right here for my y-intercept. Now let's talk about some more stuff. There are times where they don't give you a graph or a chart, and we can also still tell when something is linear. It is linear if x has an exponent value of 1. That means the variable has an exponent value of 1, so you would see just a plain x, or you would see x to the first. That's what that would look like. When it has an exponent value of anything besides 1, we say it is nonlinear. What does nonlinear mean? It means it's not a line, so this would be an example of a nonlinear function. This would be an example of a nonlinear function. Whereas we know that a linear function means a line. It looks like this. So an example for your exponent being anything but 1 would be like x squared or x cubed. Now we'll put that into practice on our next page. So here we've been asked if they're linear or nonlinear, and we're only going to circle the ones that are linear. We know the ones that are linear have an exponent of 1. So I'm going to put on every single x that has nothing next to it, just a reminder that that means there's an exponent of 1. Any other exponent is already given. So I'll make this a little larger for us, and we can see that this has an exponent of 1. This has an exponent of 1. So does this one. And this one has 2 instances of an exponent of 1, so we could combine those to give us like terms. This one also has 2 instances of exponent of 1, so we could combine it and get like terms. If I look at this one, I see an exponent of 2, that means it's not linear. An exponent of 3, it's not linear. I do see an exponent of 1 here, but I also see a -4, so it's not linear. And here I see not linear. So the circled ones are linear. Let's look at one last one before you go on to the skill. And the skill you'll be practicing will be determining if it's linear from a table. So for this one, we would do that same thing that we did for the first one. We put our inputs and our outputs. Remember, our slope is our change in y over change in x. And if it's constant, it's linear. So watch what happens. To go from 0 to 1, I'm adding 1. At the same time, to go from -3 to 1, I'm adding 4. That might be confusing to you. If you start down here at -3 and you go all the way up to 1, visually you'll see that's a change of 4. I go from 1 to 2, I go up by 1, and I go from 1 to 6, and I go up by 5. So this would be 5. Well, right away I can tell that 4 over 1 equals 4, and 5 over 1 equals 5. I need these values to be the same in order for them to be linear. They are not the same. So you would say it is not linear. Oh, I started to write yes. It is not linear. And if it is not linear, we cannot write an equation. So you could just say, I cannot write an equation because it is not linear. Now, when you plot this, you would be reaffirming what you see, and you would see that this is not linear. I need to put my x line up here so I can fit things. And I would have 0, -3, 1, 1, 2, 6, and 3, 9. It might be a little bit hard to tell that that's not linear. So there is sometimes a benefit to using a table. So when you go to do the practice that you're asked to do now, you do need to show your work. You do not need to write the whole table, but you do need to show these steps so that you have something to justify your response as you go forward. Thank you.